Let's start the session. The first presentation is weak zero knowledge via the Goldreich-Levin theorem. Kabir Tomer will present.
Hello. Okay. So, good afternoon, everyone. I am Kabir Tomer, and I am going to be presenting on weak zero knowledge via the Goldreich-Levin theorem, which is joint work with Dakshita Khurana from UIUC and Giulio Malaverta from Bocconi. So, to motivate this problem of weak zero knowledge, we will first look at a long-standing open problem, which is what is the round complexity of zero knowledge. And zero knowledge with negligible soundness error in the standard model has been known in 4 rounds for quite a while. And it is also known that it is impossible for languages outside of BBP in 2 rounds. So this begs the question that what about 3 rounds? Can we get zero knowledge in 3 rounds? And the reason we haven't been able to do that so far, the reason we haven't been able to do that so far is because of this black box barrier, which says that 3 round zero knowledge with black box simulation soundness is impossible for languages outside of BBP. So what does that leave us with? It says that, okay, either you can try non-black box simulation techniques, and all the known techniques either require 4 rounds or they require some non-standard assumptions. So 3 round zero knowledge seems a bit out of reach through those routes. So the other option is, what if you consider weaker forms of zero knowledge? And by weaker, I mean weak enough that you can still achieve them in 3 rounds, but not so weak that they're not useful for applications. And before I introduce the notion of weak zero knowledge, we'll look for a second at the standard notion of zero knowledge. And the standard notion says that there exists a simulator, says that for any verifier, for any distinguisher, the simulator interacts with the verifier to produce a view that looks indistinguishable from the view of the verifier in the real world execution. So by indistinguishable, we mean that for any distinguisher, any polynomial time distinguisher, the views look indistinguishable. And what weak zero knowledge does is it simply weakens this property. It simply switches the order of quantifiers. So instead of having a simulator that fools all distinguishers, we say for each distinguisher, we build a custom simulator meant to fool specifically that distinguisher. So the view this simulator outputs may not in general look may not be in general indistinguishable from the honest execution, from the real world execution, but it will be good enough to fool this particular distinguisher. So the thing I want to stress is that weak zero knowledge is not really that weak. So zero knowledge is typically used to enforce honest behavior. For example, you commit to some string X and you want to prove some property about X. Like you commit to a candidate in an election scheme and you want to prove that your candidate is well formed, it is a valid candidate. Or in more protocol settings, you might want to do something like commit to the same bit n times in parallel, and then prove that all those commitments are to the same bit. And in these cases, zero knowledge simulation is used to achieve some indistinguishability-based notion of security, and crucially, not a simulation-based notion of security. So we use the full power of simulation to get indistinguishability. And in these cases, weak zero knowledge also suffices. It also can be used to imply these indistinguishability-based definitions, because in those definitions, we say, okay, there exists a distinguisher that tells the difference. And then we can build our simulation strategy depending on that distinguisher. So more specifically, weak zero knowledge implies extremely useful notions such as witness hiding and strong witness indistinguishability. And in fact, weak zero knowledge is the only known way to get strong witness indistinguishability and witness hiding, apart from just regular zero knowledge. Can you still hear me when I stand like this? It's a bit unclear. Can someone at the back? Okay, thank you. We look at some previous constructions of 3 round weak zero knowledge, and those involve either black box techniques like from unlevered FHE, or in a slightly relaxed setting, which is a non-adaptive setting where the verifier's challenge is not allowed to depend on the instance being proved X. In this setting, we have constructions from random self-reducible PT, from statistically centered private OT, and the construction from factoring as well. And one thing to note, all the generic assumptions here, all of them require encryption with some homomorphic structure. It's a very vague statement, but in some way there is some self-reducibility or some like homomorphic property that is being exploited. And our goal was to understand which generic assumptions can imply weak zero knowledge, specifically whether this homomorphic structure is crucial, whether we can use techniques that do not rely on homomorphism. And we answer this in the affirmative by saying we get 3-round weak zero knowledge from trapdoor permutations. Actually, that's not exactly correct. Precisely, we get non-adaptive distributional 3-round weak zero knowledge from doubly enhanced injective trapdoor functions, which is slightly different from trapdoor permutations. And I'll not explain these adjectives too much, but the important thing is this notion of weak zero knowledge that we achieve is the same notion that these previous works have been achieving. So this notion also suffices for applications. And now I'll go into how the construction works. And the key idea for this work, and indeed for our previous works, is we construct a proof system such that verification requires some secret trapdoor that the verifier does. And if the verifier does not use this trapdoor, or if some other party tries to verify without knowing this trapdoor, then real and fake proofs look the same, by which we mean to say there is some dummy distribution of proofs that we can sample from that looks just like honest proofs. So you need the trapdoor to verify correctly. So now, when we are trying to build our simulation strategy that depends on our distinguisher, we can divide our distinguishers into two types. One is the not so intelligent type that does not use the trapdoor at all. So it does not check the proofs, does not use the trapdoor to check. In this case, this adversary can be fooled just by using the fake proofs, the dummy proofs. The adversary cannot tell the difference. This is the trivial case, it just doesn't. The more interesting case is if the adversary does check the proofs, in which case we cannot just use the fake proofs. But in this case, we can use the simulator can use the distinguisher to extract some secret trapdoor. And we will see that this trapdoor is an indirect trapdoor that can be derived from the first one, but we'll see those details. Some secret trapdoor will be extracted. So now we start actually building our proof system. We have a prover, we have a verifier. And what the prover verifier will do, verifier will send over some public key, and the prover will send over E, which is an encryption of 0. And the encryption scheme will be such that there is some secret trapdoor that the verifier knows that allows it to be. And along with this encryption E, the prover will send over witness indistinguishable proof of this statement that E is either an encryption of 1 or X belongs to it. And I claim that this proof system, which is not very interesting right now, this proof system is sound at least. Reason it is sound is because any honest verifier, the first thing that it should do, it should check the encryption E, check that it is actually an encryption of 0 by decrypting it using the trapdoor. And once it knows that this is an encryption of 0, it knows that the prover will have been forced to use a witness for the second branch of the witness indistinguishable proof, because the first branch is simply false. So if the witness indistinguishable proof verifies, then it must be using the second branch. So it cannot be cheating. So now we start building a simulation strategy for this. And we start with our first class of distinguisher that does not check the encryption, does not use the trapdoor. In this case, suppose our simulator just sends over encryption of 1 instead of 0. The distinguisher, because it's not checking the encryptions, cannot tell the difference between these two operations. In this case, it is very easy for a simulator to fool this distinguisher. It can switch from using witnesses for the final branch, for X belongs to L, and it can switch to using witnesses for E is an encryption of 1, because that is a true statement. And because of the witness indistinguishable property of the proof, no distinguisher can tell the difference. So this is the trivial case. More interesting case is what if the distinguisher does use the trapdoor to decrypt, in which case it can tell the difference between these two. So our simulation strategy won't work, but now our simulator has access to a distinguisher that can distinguish between encryptions to 0 and encryptions to 1. And we will use such a distinguisher to extract a trapdoor. How will we use this distinguisher? I will open up our simulation strategy a bit. So the simulator is just going to execute a proof with the verifier, the same as before. And what happens when it feeds this view that it generates to the distinguisher? The distinguisher is distinguishing between words where this is an encryption to 1 and words where it is an encryption to 0. So suppose in this word it outputs a 1, and in the next word where we switch it with encryption to 0, it outputs a 0 with some probability. So in these two words, basically what the distinguisher is giving us is a box that decrypts ciphertext. Specifically, we can imagine instead of the simulator generating the encryption themselves, they could receive from outside some encryption of a bit B. And to find out what the bit B is, they could execute this protocol, and the distinguisher, with some probability, is going to, some good enough advantage, is going to spit out the bit B. And if the distinguisher is in fact distinguishing, then the simulator can decrypt encryptions with probability better than ours. This is a non-trivial ability because the prover, even a malicious prover, cannot do this by the security of the encryption. So already our simulator has some power that the prover does not. And we want to somehow exploit this power to allow the simulator to simulate. To do that, we must instantiate our encryption, and we will instantiate it using trapdoor permutations. So let that IK be an index key for the permutation, and tau be the corresponding trapdoor for trapdoor permutation. And our encryption scheme essentially is we will encrypt a bit B by XORing it with the Goldreich-Levin hardcore bit for this function. So what that means is we sample a random Y, sample random R, and we write the inner product modulo 2 of Y and R. And we use that as a mask to hide this bit. And the details I'll not go into, but by Goldreich-Levin list decoding, what this means is inverting some value f of y reduces to distinguishing between these two encryptions. So any machine that can, with good enough advantage, distinguish between two encryptions of this form can be used in some Oracle fashion by querying it, can be used to invert this value f of y. And this simulator exactly has this power. It has this box to which it can feed encryptions, and the box will tell it what the decryption is. And because it has this box, we can apply Goldreich-Levin list decoding to this to get a box that allows us to invert f of y values. So we had a simulator that could decrypt, get like 1-bit decryptions, and from that we have reached a simulator that can actually find inverses, which is like a search problem. And this is more useful. Now we can start inserting this into our proof to get ways to simulate. And how we will use this ability to invert? Well, we will simply add a branch to our witness indistinguishable proof. So this is our proof from before. I have just instantiated the encryption. Nothing has changed. So what we will say is, the red part is the next one. What we will say is the verifier sends over a challenge R1. And in the witness indistinguishable proof, we add another branch that says either encryption of 1 or X belongs to L or new branch. Prover knows the inverse of R. And just a sanity check, this construction is still sound because verifier checks it's an encryption to 0, so the first branch cannot be used by the prover. And because of the hardness of the inversion, the prover cannot find an inverse for a randomly chosen R. Now, what can the simulator do on the other hand? The simulator receives a randomly chosen R1. It can, using this R1 basically, feed this R1 into its inversion box and receive this inverse. And once it has received this inverse, it can construct a fresh proof using the third branch. And that proof will convince the distinguisher because it will just look like an honest proof by witness indistinguishable. There is a slight problem. And the problem is that this R1 that the verifier is sending can be maliciously chosen. We need R1 to be uniform or something like that for Goldreich-Levin to work. And in this case, R1 will be chosen, could be chosen maliciously. So it could be that selectively for this R1, this box doesn't work. And there is a fairly simple fix for this. The fix is that we do coin flipping. Specifically, in the beginning of the proof, the prover sends over a commitment to some random value R0. The verifier still sends the index key and R1. And now the target value that we are trying to invert instead of just being R1, is R0 XOR R1. Now, we made a change to the proof, so another soundness check. No matter what R0 the prover commits to, R1 XOR R0 will still look random in its view. It still cannot invert. The simulator, however, now gets some benefit, which is by committing to random R0s, this R1 XOR R0 term is no longer like completely in the verifier's control. The simulator can make it look random, and it's not exactly random, but it turns out to be good enough for our for code-like 11 to work. And now this is the final proof. Now we can now the simulator can use this final branch to feed into this this final witness to feed into the third branch of the witness indistinguishable proof, and it is able to output convincing proofs. So that is how you get 3-round weak zero knowledge from trapdoor permutations. There are some details that are still a bit missing, specifically like how do you get it from trapdoor permutations to doubly enhanced injective trapdoor functions. I am not going to go too far into those details. I'll just close by talking about some open problems that are still there. The first problem is, well, we have the specific type of injective trapdoor function. Can we get weak zero knowledge from just generally injective trapdoor functions, or even from just public key encryption? Because the notions that we are using are all about extracting these trapdoors. Is injectivity and all? Is injectivity important? Is the enhancement important? The other open problem here is, can we get 3-round weak zero knowledge from one-way functions or something below public key encryption? And all these previous works require this extracting trapdoor notion. So we vaguely conjecture that maybe no, but it is unclear what the relationship is. And if what we believe is true, that we require this extracting trapdoor notion, which implies some kind of public key notion, then can 3-round weak zero knowledge be separated from one-way functions? And finally, the big problem that all of this is circling around: can 3-round zero knowledge be based on standard assumptions? And more specifically, can the insight we gain from building weak zero knowledge, can that help us build 3-round zero knowledge from standard assumptions? And that's it. Thank you very much.
Any questions? You can come.
I wonder, your protocol looks like that it is delaying input. Is that true?
Is delayed input, yes. So if I go back to yeah, non-adaptive, which is this setting here, where V challenge is not allowed to depend on X. So yes, still non-adaptive, delayed.
Okay.
So the same notion that all of these
That is there any way to conduct, the adaptive setting to each rebound?
So I think the techniques we are using kind of fundamentally rely on the verifier not knowing the instance, because we need to send many versions of the proof. It's there are some details, but also I'm not sure if the normal three. I think if you don't have delayed input, weak zero knowledge might run into the same black box barrier that causes problems for regular zero knowledge. So that's why the only adaptive setting technique we have is also non-black box. So I think like that our techniques won't work, but also just I'm not sure about this, but I think it will just run into the same barrier.
So have you still need a kind of FHE to train the adaptive?
Yeah, so this first work does in fact build it from FHE.
Okay.
So if I understood right, the reason why you didn't use just encryption, but then at some point went to trapdoor functions, is that you need to be able to check whether
like you use the distinguisher to decrypt, but you can't prove that what you decrypt is right. Couldn't you? But maybe I'm just confused. Instead of that, have something else in the in an earlier message that's basically like a hash of the true solution, and then you prove that you have that one. Or does that not make sense?
What do you mean true solution?
Well, you have this encryption.
Yeah.
And now you decrypt it, and then you prove that that I actually got what's inside there, and then you would prove that it's.
So to hash what is inside, someone needs to know what is inside, right? Like the prover themselves. So the prover doesn't know what's inside until they're done with it, and the verifier doesn't know what's inside, and importantly, because of the coin flipping. So. Basically, if the verifier knows the exact value that we are inverting, then it can choose to behave honestly for everything.
Yeah, I think I got it. I was thinking of having an additional component that contains the true value, but we can't even trust the verifier, so that doesn't make sense.
So no one knows the true value. So.
Okay, thank you.
Strange but true. Thank you. Okay, so the next talk, simple and efficient framework of proof systems in foreign key, and Yu Wang will present.
Thanks for the introduction. Hello everyone, my name is Yu Wang from USDC. Our title is a simple and efficient framework of proof systems on key. It's a joint work with Jiaxin Pan, Jiaxin Pan and Yuchen. In this talk, we focus on two types of proof systems. The first one is NISC, which is short for non-interactive zero knowledge, and the second one is ARP, which is short for non-interactive partial arguments. I'll talk about the first one. So here is the definition of NISC. In this work, we focus on NISC for OMP. For any polynomial size circuit, which is denoted by C here, a NISC for OMP can be used to prove that there exists some variance which is denoted by W, such that CW is equal to 1. There are three algorithms in the proof system. The first one is the generator, which includes the security parameter and outputs the CRS. The second one is the prover, which includes the CRS, the statement C, and the witness W, and outputs a proof, which is denoted by pipe. And the verifier can check the validity of the proof in a public way. It's required to satisfy three properties. The first one is completeness, which says that the proofs must pass the verification. And the second one is soundness, which says that it's difficult to find the valid proof for any invalid statement. The third one is zero knowledge, which says that the proof reveals no information on the witness except for the statement itself, which also means that there is a simulator consisting of the two algorithms, which can be used to simulate the CRS and the proof without meeting of the witness. Till now, there have been several NISCs for OMP proposed based on many assumptions, such as the trouble permutation leading, LWE, or some non-procedural assumptions, or maybe some special assumptions, such as the CH assumption in subgroups. And in the pairings under standard assumptions, the construction proposed by Gross, Ostrowski, and Saha in 2006 is still the state of the art. So it's natural to ask whether it's possible to improve the efficiency of this important and willing construction without making any trade-off. Actually, it's been more than 70 years, and there was still no positive answer to this question until our work. So in this work, we propose a pairing-based NISC, which is for OMP with shorter proofs and also less proving and verification cost compared with the JS NISC. In this work, for the NISC, we focus on the type 3 pairing since it's the most efficient type amongst all types of pairings. And our underlying assumption is the matrix DH assumption, which is a generalized version of the DH assumption. Here notice that the original GOS needs was not based on the integer assumption, but we can easily change it to be based on this assumption as we show in the paper. Please check details in our paper. We briefly talk about the construction of the GOS needs. In the construction, the prover takes as input units, which consists of bits from W1 to WI plus 1 here, and also a statement, which is represented by a circuit. Without loss of generality, we assume that the circuit consists only of NAND gates. At first, the prover extends the witness to consist of bits of all wires. And one can see that if the witness is valid, then the output must be input 1. Then the prover commits to all the wires by making use of an IT to homomorphic commitment scheme. And for the output wire, it's a little bit special. It makes the commitment as a fixed commitment to 1, which is denoted by E here, and everybody can check it in the public. The commitment scheme is required to satisfy the hiding property, which means that the commitments will reveal information on the wires. And also there should be a tracker which can be used to extract the committed values. Actually, such a commitment scheme can be easily constructed based on the indicator assumption. Next, for each NAND gate, the prover proves that the input and the output commitments satisfy a relation supported by the output. The output is just a special needs which supports the four languages. Specifically, assume that the input commitments are CMI and CMJ, and the output commitment is CMK. Then the prover proves that CMI plus CMJ plus CMK minus 2E, where is the fixed commitment to 1, as we mentioned before, commits to 0 or 1. And CMI, CMJ, CMK commit to 0 or 1. Then the verifier can just check that all the outputs are valid. And also it checks whether the output commitment is indeed the fixed commitment to 1. So this is the construction. The zero knowledge of this construction follows immediately from the hiding property of the commitment scheme and also the zero knowledge of the underlying output. Soundness follows from that when the commitment satisfy this relation, then the committed values, which are denoted by Wi, Wj, and Wk, where Wi, Wj are the inputs and Wk is the output, satisfy this relation. Wi, which says that Wi plus Wj plus Wk minus 2 is a bit. And also Wi, Wj, Wk are binary. The right part ensures the wire validity, and the left part ensures that when wire validity is guaranteed, then the input and output will both satisfy the NAND relation. Then we can extract value witness from any value proof, which proves the sumness. This is how the GOS works. And our technique to improve this construction is to make the prover prove another relation of the commitments, which is also supported by the output. So specifically, the prover proves that E minus CMI minus CMK commits to 0, and E minus CMJ commits to 0, or E minus CMK commits to 0, and CMJ commits to 0. And one can check that the cost is less. I mean, the verification and proving cost will be less if we adopt this new relation. And one can also check that the gate consistency is satisfied. Specifically for the committed values, we have 1 minus Wi minus Wk is equal to 0. This corresponds to this part. And 1 minus Wj is equal to 0. Or 1 minus WK is equal to 0 and WJ is equal to 0. And one can check that to satisfy the NAND relation if everything is binary. But the problem is that the wire validity is not guaranteed, which means that the committed values may not be binary. For example, when Wj is equal to 1, then Wi and Wk might be some large numbers with the sum happening to be 1. For example, if the size of the field is 13, then Wi might be 5 and Wj might be 9. And one can check that the sum is still 1, but obviously they are not bits, so it's not valid. Also, when Wj is equal to 0, like this, then we make no restriction on Wi, so Wi can be any large value. So a simple solution to this problem is to additionally prove that the permitted values are indeed bits, but this will make the construction less efficient than the GOS needs, which makes no sense. So our solution is to propose a new Venus extraction strategy. By making use of this strategy, we can prove that to extract a value Venus, we actually do not need to prove the wire validity. As long as the committed value satisfy this relation, we can extract the value Venus. We'll now show how it works. When the proof is valid, as we mentioned before, the final output commitment should be a fixed commitment to 1. So the committed value must be 1. Then if the right input is equal to 1, then according to this relation, G5 is equal to 1, which is a binary. Then the left input should be 0. You can easily check it. So everything is binary now, and there's no problem now. The problem is that if the right input is equal to 0, then according to this relation, the left input could be any large value, so we cannot assign values to it. Our strategy is not to assign any value to it. We just leave it as blank for now. And one can check that. This is a key observation. One can check that no matter what values are assigned to the subtree, which outputs this wire, G5 will output 1 anyway, because its right input is 0. And it's a NAND gate, so its output must be 1. Then next, for the output of G4, it's also the right input of G5. It must be binary according to this relation, since Wj must be equal to 1 also. Then we can assign values to its input wires in the same strategy. Eventually, we can obtain part of the wings. And the point is that no matter what the rest of the input wires are, I mean, they are left as blank for now, the assigned values will lead the circuit to output 1 anyway. Then by setting the blank wires as 0, or maybe some other binary values, we can obtain the wings. This is how it works. Now for better understanding, I give a more concrete example. Without loss of generality, we can assume that the right inputs of G1, G2, G4, and G5 are 0, 1, 1, 0. Then as before, the output of G5 must be equal to 1. Next, we leave the subtree as blank. Then for G4, according to the left part of the relation, its left input must be equal to 1. And for G2, also according to this part, its left input must be equal to 0. And for G1, according to the right part of the relation, we do not make any restriction on Wi, so its left input is left as blank. Now we get the wings, which is blank, 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 0, 0, 1. Then by setting the blank wires as 0, we can obtain the wings, which is 0, 0, 0, 0, 0, 1. You can check that this is right. And actually, it can also be 1, 1, 1, 0, 0, 1 as well, because the first 3 bits do not affect the final output anyway. And this is our idea. And next, with the comparison between our needs with the GLS needs. In this table, T represents the number of wires and S represents the number of gates. And one can check that T must be larger than S in any circuit. And in this table, we can see that our proof size and proving and verification cost are strictly smaller than the GLS needs. This is the experimental result, and it's consistent with the table in the previous page. One can see that when the ratio between the number of gates and wire is 2, then our proof size is 1.6 times smaller. And our prover is about 1.5 times faster. Our verifier is about 1.4 times faster. So this is our result on the needs. Next, we talk about the result on the ARC, which is the non-interactive partial argument. Here is the definition of ARC for 1P. It's a little bit complicated, so we omit the details and just mention that the ARC for 1P can be used to generate a proof for many NP statements in the same time, where the proof size scales sublinearly with the number of statements. And for the bar, zero knowledge is not required. And we just consider the case that the proof size is independent with the number of the statements. I know there have been several bugs for NP proposed. And in the pairings based on the standard assumptions, which can be MDD feature assumption for the subgroup decision assumption, the construction proposed by Waters and Wu is still the state of the art. And in this work, we propose pairing-based parts for NP with shorter proofs and less proving and verification codes compared with the WW part. Our assumption is the same, which can be the MDDH assumption or the subgroup decision assumption. And we make no trade-off, just like our needs. We briefly mentioned our idea for this. Actually, the technique is similar, but a little bit different. At first, the same as before, the prover extends the witness to consist of the piece of all wires, and then it commits to all the wires. Anything of a vector can not, and writing property is not required here. Next, the prover generates succinct proofs for each NAND gate for the wire validity and the gate consistency. And if we can use we can prove the gate consistency of the wires by making use of the relation used by our needs, then we can also reduce the cost of this construction in the completely same way. But to do this, we need a batch-all proof. But the problem is that we do not have an explicit batch-all proof. So our technique is to, at first, prove a nonlinear relation for each NAND gate, and then prove that this relation implies a more relaxed version of the OR relation. Actually, this is the OR relation. This part is very similar to our NISC, and this is an additional case. We now give, and then we can use a generalized witness extraction strategy to extract the witness for proving the sumness. We give a simple example for this. Same as before, the output must be 1 if the proof is valid. And then if the right input is equal to 1, then the left input is equal to 0 according to the relation. This is the same as our needs. But the difference is that for some gates, the left part might be determined at first, and when it's 0, this part is left as blank. I recall that in our needs, the left input wires are always binary. And then we can continue to extract the value for G1, and eventually we can obtain part of the winning size before, which will lead the circuit to out to one anyway. Then we can set the blank wire size 0, and we can obtain wins. Here is the comparison. Our proof size and proving and verification cost are smaller than the WW bar in both the prime order and composite order groups. And when the ratio between the number of gates and wires is true, our proof size is about 1.2 times smaller. And when proving 100 statements in the same time, our prover is about 2.2 times faster, and our verifier is about 2.7 times faster. So this is our result. And here are some extensions. By making use of the converging technique proposed by GOS, Ostrowski and Sahai, we can convert our NISC to a non-interactive ZAC, which is the most efficient based on the standard assumptions in the pairing, for now as far as we know. And by making use of the converging technique proposed by Kalai and others recently, and also some technique by Waters and Wu, we can convert our bar to a SNARP 4P, and it's also the most efficient in the pairings based on standard assumptions as far as we know. So this is the extension, and here is the conclusion of our work. We proposed a simple and efficient framework of proof systems for MP, and we can make use it to improve the efficiency of the GOS NISC and the WW bar without making any trade-off, which means that our constructions are truly more efficient than theirs. And any application of their applications should use our constructions instead. Thank you.
Questions?
Thanks for the talk. So in the talk, you talked about just doing NAND gates. In the actual paper, do you anything besides NAND gates? Like general, like you give me a Boolean circuit, whatever. Or do you just convert it to NAND gates and take that one?
Next question. Actually, in practice, we do not have to convert the circuit to a circuit consisting only of NAND gates. Actually, the NAND gates can also be an AND gate. And we can also use OPU to prove the relation of the commitments. We just need to slightly modify the relation satisfied by the committed values, and the OR relation is also the same. So we do not have to convert it. We just do it.
We just use none because it's universal.
Yeah. And
It makes the interaction simple.
Yeah.
Thank you.
Anybody who wants to ask a question, come forward. Save time in the gym.
Thanks, Bruno. I was wondering in the last slide, the conversion that you're showing for a smart group, is this like do you do it actually efficient, non-black box, or you apply the general strategy, which uses like CF hash and so on?
Actually, it's sort of black box. Yeah, actually, we really didn't have to do anything about this. We can just use the results by.
But what I mean is, if you instantiate it also over pairings, or if you use it like generic CI hash.
I think it's also in pairings.
Okay.
So thank you very much.
Thank you.
Okay, so let's move to Sigma protocols for verifiable secret sharing and their applications, and Min Jiang will present.
Thanks for the introduction. Let's start with the background. A Sigma protocol for a relation app is a three-move and fully interactive group system between a prover and a verifier. It sets basic properties, complexity, special service, and special honest, verifier zero knowledge. That's the specific property. Protocols have many adaptive properties. For example, they are efficient for algebraic statements, and they are very efficient classic SQL protocols, including the small automata and GPU protocols. They can be easily combined with component statements, such as the AND or statement. Third, they provide a simple way to establish proof of knowledge property. Or they can be made non-interactive via the fiat heuristic, and they enable numerous real-world applications. Due to these attractive properties, Sigma protocols have received much attention. However, many previous works aim at improve their efficiency or enrich the functionality. Their attentions were paid to the generic construction of Sigma protocols. These classic Sigma protocols are ingenious but handcrafted. It's curious to know whether there exists a common design principle of Sigma protocols. To our knowledge, Morris' work is only one in this direction. He proposed a framework of zero-knowledge proofs for group homomorphisms. It unifies a substantial body of works. However, Morris' work has it even failing to explain some simple variants of classic protocols, such as this simple variant of Snow protocol. As we can see, the initial message could be computed using a different group homomorphism then, and the response can be computed using a different way. Therefore, the machinery of Sigma protocols is still unclear. Based on the above discussions, we are motivated to answer the question: is there a more generic framework of Sigma protocols? Look at this celebrated Snow protocol. It looks very simple. Could you see the underlying design principle of it? Our starting point is the NDC is a head paradigm proposed by Isha and others in 2007. In a nutshell, to prove the knowledge of W such that CW equals to 1, where C is either an arithmetic or a Boolean circuit. The prover first shares the witness W into n shares using the XOR-based secret sharing scheme, and then runs the corresponding NDC protocol and obtains the views of all parties. Then he commits to all the views. After that, he sends the commitment to the verifier. The verifier picks a random subset I from the index set and sends I to the prover. The prover replies with corresponding views. The verifier accepts if and only if all the commitments are opened successfully, all the outputs are 1, and all the views are consistent with each other. An important fact is that the MPC in the head is a Sigma pattern protocol for arithmetic statements. It leads us to think that since algebraic statements are arguably simpler than arithmetic statements, when scaling down to algebraic statements, we may start from a light machinery than NDC. We finally found the verifiable secret sharing scheme, DSS, is exactly the right machinery. It was first proposed by Cole and others in 1985. Feldman then gives the notion of non-interactive DSSE, which consists of 2 phases and 5 algorithms. In the sharing phase, the dealer holding a secret W First runs the encrypt algorithm and broadcasts ciphertext C. And then he runs the share algorithm and obtain the shares. And he sends each share to each party privately. After receiving the shares, each party checks whether they are valid via the check algorithm. In the reconstruction phase, honest parties can recover the secret W via the recover algorithm. A VS scheme should satisfy three properties. First is the acceptance. Valid shares always pass the check. Second is the TP privacy. A group of no more than TP shares leaks nothing about the secret W. Third is the consistency. A group of no less than TF valid shares indicates that there exists a unique secret W and it can be recovered by pulling enough valid shares. Before giving the framework, we present a refined definition of VSS. It differs from the previous one in both syntax and properties. In the syntax, we decompose the share algorithm into two parts. First is the count algorithm, which on input a secret W and a randomness R outputs a commitment C. Second is the share star algorithm, which on input a secret W and the randomness R outputs N shares and the authentication information auth. It will later be used in the check algorithm. In the properties, we do not stipulate the consistency property as previous. We introduce a new notion, TF correctness. It requires that by pulling no less than TF valid shares, we can recover the secret W and the randomness R, and there must be an opening of the commitment C. Now we are ready to construct Sigma protocols from VSS. To prove the knowledge of an opening of the commitment X, the prover acts as a dealer holding a secret W and a randomness R, and the corresponding commitment X runs the share star algorithm in his head to obtain the authentication information auth and N shares. After that, he sends auth to the verifier. The verifier picks a random TP-sized subset I from the index set and sends I to the prover. The prover replies with corresponding shares VI. The verifier accepts if and only if all the shares are valid. The completeness follows from the acceptance of the underlying VSB. The special soundness follows from the correctness of the underlying VSB. The essence physical property follows from the TP privacy. Our framework not only neatly explains classic Sigma protocols, but also gives a generic way to construct Sigma protocols. We first show how it explains the celebrated snow protocol. Given the Feldman's VSSB with a number of parties N, the privacy threshold 1 and the fault tolerance threshold 2, we can construct the Sigma protocols for proving knowledge of a discrete operation as below. The prover acts as a dealer holding a secret W and the corresponding commitment X. First, it determines to share W through this random polynomial HI and computes the authentication information A by committing to the constant. After that, he sends A to the verifier. The verifier picks a random index I from the index set. The prover then computes the corresponding share VI, which equals to HI, and sends VI to the verifier. The verifier accepts if and only if the following equation holds. By setting N to the size of CP, we immediately recover the Sigma protocol. Our framework also yields new Sigma protocols. For example, instead of using the Feldman's VSB, the prover could also use the additive VSSB with a number of parties N, privacy threshold N-1, and fault tolerance threshold N. It's obviously a Sigma protocol for discrete logarithm with two special sizes. A further question is that, is there any other application of BSS in the head? Let's start with some background photos. In the realm of zero knowledge proofs, there are three types of statements. First is algebraic statements, which are usually proved via Sigma protocols. Second is non-algebraic statements, which are usually proved via general problem CPPs. Third is the composite statements, which combine algebraic and non-algebraic statements in arbitrary ways. Among them, the commit and proof is the most common type. Concretely, the prover wants to prove that he knows a witness W such that count W equals to X and CW equals to Y, where I is an algebraic commitment and C is either the arithmetic or Abelian circuit. To prove such a statement, the naive method is that first homogenize the form and then use only Sigma protocols or general problem CPPs to prove it. In one direction, we can transform the circuits into algebraic constraints by expressing each gate as the algebraic constraints between inputs and outputs. However, it will make the number of both public key operations and group elements linear to the certain size. In the flip direction, we can transfer the algebraic constraints to circuits. However, it will make the size of the statements dramatically increase. Therefore, both directions introduce significant overhead. A better method is that we can use Sigma protocols to prove the algebraic part and use general problem CPPs to prove the non-algebraic part. It takes the advantages of both Sigma protocols and general problem CPPs. However, in this case, a malicious prover could generate Pi1 and Pi2 using different witnesses. Therefore, many previous works focused on designing group proofs to link these two parts. Thus, that the prover is enforced to generate these two groups using a consistent witness. However, group proofs inevitably incur additional overheads in both computation tests, and group proofs must be tailored in a specific way to align with general purpose CPPs, thus requiring extra design efforts. An intriguing question is whether the seemingly indispensable group proofs are necessary. Below, we show how our BSS in the head paradigm gives rise to a generic construction of CPPs without group proofs. Our main observation is that both the BSS in the head and the MPC in the head paradigm share the same Sigma pattern and the same secret sharing scheme. A high-level idea is that when we're using the witness sharing procedure, the prover is enforced to use a consistent witness without group proofs. However, when realizing these high-level ideas, we encounter two technical obstacles. First, the secret sharing mechanism in the MPC in the head protocol sticks to the XOR-based SSD, making it hard to interact with general BSS schemes. Second, the relationship between BSS and SS is unclear, making it difficult to reuse a common part of witness sharing procedure. To tackle the first issue, we give a generalized version of MPC in the head. We extend the XOR-based SS scheme to a general SS scheme, and formally proves its completely special size and SS properties. To settle the second issue, we give the notion of separable BSS to establish a relation between BSS and SS. Informally, we say a BSB satisfies separability if its shared style algorithm can be dissected as below. Thus, broadly speaking, the procedure of generating shares and the OR can be separated. And each share VI can be separated as into a share of secret WI and a share of randomness RI. If there are If they are computed as per some secret sharing scheme SS, then we say this BSS scheme aligns with that SS scheme. And now we are ready to combine these two parts. We use the sigma protocols from BSS to prove the algebraic part, and use general purpose CKPs from MPC in the head to prove the non-algebraic part. If the BSB in the left aligns with SSB in the right, then they can be combined directly to prove composite statements through witness sharing reusing. The prover is enforced to use a consistent witness. The whole protocol is shown in the figure. As we can see, the share algorithm and the challenge I and the trust of witness WI are reused. Our construction has the advantage of requiring no proof proofs, being public and transparent. We finally give an instantiation from Liberal protocol via two steps. First, we identify the SS being used in the Liberal class. Second, we construct a BSP that aligns with this SSP. Our instantiation also solves the open problem left by papers in 2019, achieving a more compact proof for composite statements. In summary, our contribution is twofold. First, we give a framework of sigma protocols for algebraic statements, which not only neatly explains classic sigma protocols, but also gives a generic way to construct sigma protocols. Second, we give a generic construction of CKPs for commit and proof type composite statements, which has advantages of requiring no proofs in public and transparent. That concludes our presentation.
Thank you.
Very nice talk. And I was wondering whether, so there's been a lot of effort in recent years to study, for example, these compressed sigma protocols. So basically multiple rounds of sigma protocols. So something like bulletproof falls into that scheme. Do you think your theory would also, have you looked at all if this translates to kind of these multi-round protocols, which are essentially just a concatenation of multiple sigma protocols in a row? Have you looked at that at all?
I think we haven't considered this problem, but I think if the BSB is a non-interactive version, if it's an interactive version, maybe it could explain what around.
I mean, more, sort of just protocols where that have essentially a composition of multiple sigma protocols in a row. So you use one to reduce the statement in half, and then you use another one to reduce the statement in half, and you do this, say, a logarithmic number of times. And product argument. It's okay, we can discuss later. But yeah, I would be very interested to see. I assume this could be a plan.
Just we know from classical results that ESS can be used as a distributed function. So what is the difference between just saying that we use ESS to commit and just we use MPC-based technique to prove? So what is the difference between this and your protocol? Things that you are believing, but here the commitment is just ESS.
You mean the difference between the BSS and
yeah, because you mentioned that you don't use glue to prove the statements, not the two statements that you have. But my question is, what is the difference between this using this as a commitment? why you don't, you basically the clear question, why you don't claim that you don't use believing technique for this complex statement? I don't know if you can.
Because in this way, it's trying to
Yeah, isn't it natural from the estimated technique that because you have distributed cycle, and it's not.
yeah, because they use the same the sharing scheme is the same. They share the secret.
So and any natural, natural control the signal. I think any country. Yes,
Yeah.
Because it is framework.
Yeah, exactly. Any improvement concept.
Any other question? Okay, so then all the speakers, and all the people that are standing in order to hear the talks. Thank you.
Outside.